Right, so we'll start with activity 2.2. Here, first question says choose the set of correct answers. Let's say the limit uh, h tends to 0 of f of a plus h minus f of a whole divided by uh, h exists if f is differentiable at a. So yes, this is the right option. So this is the definition of differentiation. So yes, this is correct. Second option, a function f may be differentiable at a point a even if it's not continuous at a. So let's say what is differentiation. So differentiation is nothing but let's say we have a curve something like this, and we have to check whether the curve is differentiable at this point a, let's say. Okay, it simply means that we are trying to draw a tangent at this point. This is nothing but differentiation, right? So here, let's say if the function is not continuous, so we have a function something like this. Okay, at point a, this is a, right? So let's say this is at a and this is not at a. So how can we draw a tangent for a graph something like this? So it is not possible, right? So second option is wrong. Moving on to the third option, if a function is differentiable at a point a, then it must be continuous at a. Yes, so we have already said that uh, we are trying to draw a tangent. If we are trying to draw a tangent, so that at that point where the tangent is drawn, it has to be continuous, right? So third option is right. So what about next option? There can exist some continuous functions which are not differentiable at some points in the domain. Okay. Yeah. Let's say we have a graph something like this. Okay. So let's say this is point A. We can easily say that the left hand limit and the right hand limit approaches at some point. Let's say this is f of a. So there exists a limit. But can we draw a tangent over here? Imagine we are trying to place a stick at this pointy end. What will happen to the stick? Either it will tilt, right? So it is not stable. If let's say if we are trying to place a stick for this surface, it will be stable, right? Comparatively. Why? Because there will be a smooth surface at the end. This is an exaggerated figure, let's say. So we can draw a tangent for this type of surfaces, but we cannot draw a tangent for sharp edges, right? So this, again, the function is continuous at a, but we cannot draw a tangent for this. So at f, the differentiation of f does not exist. So this option is also true. Okay, moving on. Which of the following options shows stepwise solution for the function of differentiation? Okay, so the first function is constant. So let's say for any constant function, the differentiation of a constant is always 0. This is an important point to remember. Okay, let's try from the first principles. Let's say limit, they're already having the limit h tends to 0 f of a plus h minus f of a divided by h. What is f of a plus h? This is simply also what will be f of a plus h. For the first case, it will be nothing but c, right? It will not be c plus h. For any value of x, we will be having, it will be mapped to a single function, that is c. That is what they have given, but they have substituted c plus h. So this function value is wrong. For the second option, the given function is x minus c. Here what will be a plus h? It is nothing but in place of x we are substituting a plus h minus c minus of a minus c. So here uh, a and a, this will be cancelled, c minus c and plus c will be cancelled. So what is remaining? H by h, so that is 1. So this option is true. What about third option? Third option we have a plus h, the function value is x square. Just by saying telling about the rule, this d by dx of x to the power of n, that will be given by n x to the power n minus 1. Here n is value is 2. We can say that the value is 2x. But since we have to check the steps, let's say, simply by seeing this value and this value, we can say that this option is wrong. But where have they gone wrong? Let's see. A plus h whole square minus a square, right? So this will be a square plus h square plus 2ah minus a square. so this will be cancelled. What is remaining here is h square plus 2ah whole divided by h. If we take h common, what will we have? We'll have h plus 2a divided by h. H and h will be cancelled. What is remaining is 2a. So here h tends to 0, this value is tending to 0, what is remaining is 2a, but they have got 0. This option is wrong. What about fourth option? Fourth option, let's say we have differentiation of e to power x. Differentiation of e power x is always e power x, right? Let's see what will happen. Here e to the power of a plus h minus e to the power of a divided by h. We have, let's take e to the power of a common. We have e to the power of h minus 1 divided by h, and they have taken e to the power of h outside the limit. Since it is a constant, inside the limit it can be taken, the value inside the limit can also be taken to the outside limit. This is the rule, right? What is inside the limit now? H e to the power of h. If we substitute h as a, we have e to the power of a, sorry, e to the power of 0 minus 1 divided by 0. So that is nothing but 1 minus 1 divided by 0. Again, what is remaining? So this whole value will be tending to 1. So we have e to the power of a as the answer. So this option is true. Moving on, the third question, we have a floor and step function. Okay, f is differentiable at 0, f is differentiable at 1. Okay, let's see what will be the value of 1. So we have step function at 1, right? Okay, at 1 we know that there will be two values, right? It will be something like this, right? So something like this, but here at this point the function will not be differentiable. First option is, sorry, the second option is wrong. What about f is differentiable at -1? Even in this case we will be having something like this, right? At -1, again f is not differentiable at this value. What will happen at 1.5? Let's say if this is 2, 1.5 is somewhere here. So the left hand limit and the right hand limit exists, so there will be the function is continuous at this range, and so we can draw a tangent over here, right? So this option is true. What about at 0? Let's say if this is the axis and this is 0, the function will be something like this. Okay, that the negative x direction we have a step function, so that will be something like this. Okay, so at 0 the left hand limit and the right hand limit coincide, so we can differentiate the function at 0. So first option is also true. And moving on, consider the graphs given below. First option says f1 is continuous and differentiable at every real number. Let's check at a. At 1, so the function is continuous, the left hand and the right hand limit exists, but we cannot draw a tangent. So f is not differentiable at all the real numbers. It is not differentiable at 1. So first option is wrong. f1 is not differentiable at 1, so this is true. We just said that. What about graph 2? We have f2 is not continuous at 0. Yes, so at 0 it has the left hand limit and the right hand limit is approaching to two different values, so this is not continuous at 0. Okay, what about fourth one? F2 is differentiable in the interval 1, 2. In the 1, 2 interval, the function value is continuous, right? So it is the left hand limit and the right hand limit at each point here exists, and also it is differentiable at every point in this interval. So this option is also true. Moving on, the function is x cube, sorry, cube root of x, right? What is it is continuous on R. So for every value of x, we will have some value on y. So first option is true. What about the second one? F is differentiable everywhere on R. So at every point there is a smooth curve, right? So at every point we can differentiate R. So from the first glance we can say that, but observe at 0. What is happening at 0? We have the function value something like this, right? The tangent will be perpendicular to the x-axis, right? So this cannot be done. So it is not differentiable at 0, but at every point the function is differentiable, right? So this option is wrong, this option is also wrong. Now moving on, there exists a function f tends to R such that f is not differentiable exactly on the set of natural numbers. Yes, this is true. We have floor function as the example. Inverse of a differentiable function is differentiable. It's not necessarily true, right? F of x is equal to x square, x is rational, and f of x is equal to 0. For x irrational, f is differentiable at x equal to 0. Yes, for f of x equal to x square, this will be the function, this will be the graph. At x equal to 0, the function is continuous, so we can draw a tangent, right? Horizontal line will be a tangent. So this function, so this statement is also true. Next question, consider the function mod x. Then f is, let's draw the graph of sin x first. Sin x will be sinusoidal, something like this. Okay, now I'll simply change the color. What about mod x? Mod x will be, for the first half it traces sin x, for the next half it will be the mirror image of sin x. So it will be something like this, right? Okay, so what will be the period? Period will be, even if we say the period is 1 by 2, that will true. Again, if we say pi, for every pi the function repeats, right? So this is true. Everywhere function is continuous, so everywhere the function is continuous, but what about at these points, right? At n pi, let's say, okay, at all n pi's, so this function is not differentiable. Okay, so this option is wrong, but this option is true. But it is continuous but not differentiable, so this option is also wrong. Moving on, this is the graph. So they are said something about the graph. There are some points in the interval -5 to 5. We are considering this interval, okay, at which the derivative of f is 0. There are some points in the interval -5, 5 at which the derivative of x is 0. Okay, let us consider these points. At these points the derivative will be 0, right? This option is true. There are some points in the interval -5, 5 at which f is not differentiable. So observe that there are no sharp points here, right? There are no points of discontinuity also. So second option is wrong. What about third one? F is not differentiable at 0. Again, at 0 the function is continuous, there are no sharp points, and the left hand limit and the right hand limit approaches the same value, but that is this is also false. There are at least 2 points where the derivative of f are non-zero but the same. Okay, observe this point here and also this point. These two tangents will be parallel, right? So this option is also true.